Most people only ever interact with statistics for a limited part of their lives, but statistics is a field of research. Like other areas, statistics has evolved. Influential ideas have come and changed the trajectory of statistics. As a student of biostatistics, it's my responsibility to be familiar with these revolutionary ideas in the field. In this video, we'll talk about 8 innovations in statistics that have shaped how we know it today, and I'll do my best to explain what these innovations are and why they were so impactful in a way that makes sense to a general audience. If you're new to the channel, welcome. My name's Christian. My goal is to make statistics accessible to more people so that they can apply it to their daily lives. In 2021, Andrew Gelman and Aki Vettari published an article in the Journal of the American Statistical Association, or JASA. JASA is one of the most prestigious journals in the field of statistics, so publishing here is a big deal. But instead of a research manuscript, Gelman and Vettari publish an essay. This essay is titled, "What are the most important statistical ideas in the past 50 years?" And this article is what motivates this video. But 2 statisticians do not make up an entire field of statistics. So what gives these 2 authors the authority to answer such a question? The essay was meant to be thought-provoking, not authoritative, though I would argue that both Andrew Gelman and Aki Vettari are in fact authorities in the field. They are widely known among practitioners of Bayesian statistics since they basically wrote the Bible on it, Bayesian data analysis. As of the writing of this video, Andrew Gelman is a professor at Columbia University in both statistics and political science. Aki Vettari is a professor of computational probabilistic modeling at Aalto University in Finland. Andrew Gelman also maintains a fantastic blog on statistics, political science, and their intersection, which I highly recommend. The article considers statistical innovations that happened from around 1970 to 2021. So this is the time period for which I call modern statistics. Without further ado, let's have a look at the list. In an ideal world, all data comes from experimental data, where a researcher can control who receives an intervention and who doesn't. When we can do this in a carefully controlled manner, such as in an RCT, we can claim cause and effect between an intervention and some outcome of interest. But we live in the real world, and the real world gives us observational data sometimes, where we can't control who receives a treatment and who doesn't. We can still perform statistical analyses on observational data, but we cannot make the same causal claims about them, only correlational claims. This was until counterfactual causal inference came onto the scene. This framework allows us to take observational data and make adjustments in a way that gets us closer to causal statements. How this works is the topic of an entire other video, so I'll give you the basic breakdown. Let's consider a world where I have an upcoming test. I can choose to study a bit more, or I can choose not to. In this reality, I choose to study, and I get some score on the test later. I'll denote this as y sub 1. If a supernatural statistician wanted to know if this decision caused the change in my score, then they would have to examine another reality. They would have to find the reality where I didn't choose to study, and measured the test score of that version of me who didn't study. I'll call that outcome y sub 0. The only difference between these 2 versions of me is that I chose to study in one, but not in another. This unobserved version of myself is called the counterfactual, because this version of me is counter to what actually or factually happened. Then, the causal effect of me studying on my test score is the difference between y sub 1 and y sub 0. The fundamental problem in causal inference is that we can only ever observe one reality and therefore one outcome. In essence, it's a missing data problem. The counterfactual framework is important because it helps give statisticians a way to formalize causal effects in mathematical models. This is significant because several fields of study are prone to having more observational data, such as economics and psychology. If you've been with my channel for a while, you may be familiar with this one already. That video delves into more technical detail, but I'll briefly explain what it is in this video. The bootstrap is a general algorithm for estimating the sample distribution of a statistic. Ordinarily, this would require gathering multiple datasets, which no one has time for, or it would require mathematical derivation, which I don't have time for. Rather than do either of these, the bootstrap takes the interesting approach of reusing data. From a single dataset, the bootstrap generates several bootstrap datasets by sampling with replacement from the original. For each of these bootstrap datasets, a statistic of interest is calculated, and their distribution can be derived from this entire collection. This is incredibly valuable not only because it's super simple and therefore easy for more people to use, it's applicable to many kinds of statistics. We can use Bootstrap to create confidence intervals for point parameters like a regression coefficient, or we could create confidence bands for coefficient functions, like we might see in functional data analysis. The Bootstrap is significant not only because of its usefulness, but because it highlights the significance of computation in statistics. A quote from one of my heroes is very relevant here.
You see, killbots have a preset kill limit. Knowing their weakness, I sent wave after wave of my own men at them until they reached their limit and shut down.
Instead of human life, statisticians can do a lot just by using wave after wave of our own computer's processing power. The rise of computational power has made it easier to perform simulations, and simulated data allows us to assess experiments and new statistical models. For example, simulations can be used to assess power and type 1 error of experimental designs for clinical trials, without actually needing to run them. This means a lot of money and effort is saved for pharmaceutical companies. Another example of simulation-based inference comes from Bayesian statistics. Bayesians encode knowledge in the form of priors, or probability distributions on parameters. Using these priors, we can actually simulate data from a prior distribution and check if the resulting data we collected actually makes sense here. This is called a prior predictive check. The same can be done for the posterior distribution of a parameter, which makes it a posterior predictive check. And these are incredibly useful for validating our models. To understand this idea, we need some context on statistical parameters. One way to view parameters is that they are representations of ideas that are important to us within statistical models. In a two-sample t-test, the mean parameter represents the difference of two groups, such as a placebo and treatment group. In linear regression, we're interested in the coefficient associated with treatment, which represents the associated change to the outcome that the treatment has. Statistical models are approximations of the real world, but we can actually change our models to match the real world a little better. One way we can do this is by increasing the number of parameters that are in the model. Consider the simple linear regression. It tells you that the distribution of an outcome shifts according to this coefficient. But what if we expect this change to vary over time? In the current model, there's no parameter for time, so this model simply can't capture this complexity. We can move up a level by incorporating more parameters into the model and adding a coefficient for both time and the interaction between time and treatment. But what if we suspect that each individual in the study will react differently to the treatment? The current model tells us that this single parameter will explain the change for this population on average. To give everyone their own subject-specific effect, we can make the model even more complex and turn it into a mixed effect model. More parameters, more flexibility. Over-parameterized models take this idea to the extreme, make the model extremely flexible by adding tons and tons of parameters. Neural networks are a prime example of this. Each edge in a neural network is associated with a parameter, or weight, along with some extra bias parameters. We can easily over-parameterize by making these networks very large, and by doing so, the universal approximation theorem tells us that these networks can approximate a wide variety of functions. And this extra flexibility is important because it lets us model a wider range of phenomena that simpler models just can't handle. One problem with extremely flexible models is that they may start to approximate the data itself, rather than representing a more general phenomena we can learn from. Statisticians employ regularization techniques, which help to balance out this complexity by enforcing that these models maintain some degree of simplicity. Multi-level models, also known as hierarchical or mixed effect models, are models that assume additional structure over the parameters. For example, multi-level models are commonly used to aggregate several N-of-1 trials together. Each individual is associated with their own treatment effect, which I'll denote theta j, to indicate that each individual has their own effect. These individuals form the second level of the model. The first level can be thought of as describing the distribution or structure of these individual effects. In an N-of-1 context, the first level might be a normal distribution, centered at some population treatment effect theta, with some variance sigma squared. In different contexts, the units of the second level of the model could be different things. In a study taking place over many locations, these may be different hospitals or cities, something to indicate a cluster of related units. In a basket trial, each second-level unit is a specific disease, and we suspect that their treatment effects will be similar because they share a common mutation. In meta-analyses, the second-level units could be estimated effects from individual research studies. Andrew Gelman says that he views the multi-level model as a way to combine different sources of information into a single analysis. This kind of structure is incredibly common in statistics, so that's why multi-level models take a spot on the list. Multi-level models can be both frequentist and Bayesian, so why is Bayesian specifically mentioned in the article? But my guess is that the Bayesian framework allows us to incorporate prior knowledge into the models. This is especially helpful when deciding on priors for the first-level parameters, especially on the variance. If you choose a wide, uninformative prior, it encourages the resulting model to treat second-level units as being independent of each other. On the other hand, choosing a narrow, informed prior allows us to pool data together, which can help us estimate treatment effects for second-level units with small sample sizes. Being able to choose different priors gives statisticians much more flexibility in the modeling process. A recurring theme among the top 8 ideas is the importance of computers and computational power to the development of statistics. Advances in technology have allowed more complex models to be invented for harder problems. To account for this, several important statistical algorithms have been invented to help solve them. An algorithm is just a set of steps that can be followed, so a statistical algorithm is an algorithm designed to help some statistical problem. But there are so many types of statistical problems out there, it's hard to get an appreciation for how useful these algorithms are. So I'll explain two to give you a taste. The expectation maximization algorithm, or EM algorithm, is famously known from a 1977 paper in the Journal of the Royal Statistical Society, another heavy-hitting journal in statistics. The EM algorithm solves an estimation problem, which is where we need to use data to compute educated guesses about the values of parameters in a model. Maximum likelihood estimation is another example of an estimation approach. What makes the EM algorithm distinct is that it tries to estimate the parameters in a model that we can't solve directly. One instance where this can happen is in the case of mixture models with so-called latent classes. In this type of model, we have data that may come from one of several groups, but we don't have the group labels to tell us who belongs where. Without delving into the details, the EM algorithm gives us a way to still estimate the parameters in this model despite not knowing these classes. The second example is the Metropolis algorithm and its more modern descendants. The Metropolis algorithm is interesting because its roots actually stem from physics, as opposed to statistics. The Metropolis algorithm is significant because it lets us generate samples from very complex probability distributions. Random number generation according to some distribution may seem weird, but it's important for statisticians to be able to do so. The posterior distribution that comes from Bayes' rule can turn ugly if we turn away from conveniences like conjugate families. The posterior can be so ugly that we can't even derive an equation for it. But despite this, we can still generate samples from a complicated posterior thanks to the Metropolis algorithm. Even if we don't have a formula for the posterior distribution, we can still use the generated data to recover important quantities about the distribution, such as the mean, the quantiles, and credible intervals. These two algorithms are just two examples mentioned in the article. There are many I couldn't cover, and still more that have been developed since this article was written. When statisticians design experiments, it used to be a set and forget type of thing. Figure out the sample size, and just run the experiment to completion. But midway through the experiment, we might need to stop it. Under a frequentist framework, this would hurt our power and our p-value interpretation. But in modern times, we have a way to account for this. Adaptive decision analysis is the idea that maybe we don't have to wait for the entire experiment to finish. Instead, we can adapt our experiment based on data we collect in the interim before it finishes. In the context of clinical trials, we may decide to stop a trial early if preliminary evidence suggests that the treatment sucks. Conversely, if a treatment shows early promise, we can even stop based on efficacy. These changes still have to be decided ahead of time to make sure that we make good decisions overall and that the trial is well designed. Statisticians have to make a lot of assumptions. If these assumptions are right or at least plausible, then we can feel comfortable trusting the results of statistical analyses, stuff like confidence intervals or estimated values. But of course, assumptions won't always be right, and it's often hard to even know if they actually are or not. And that's where robust inference comes in. Robust statistics still provides trustworthy statistical analyses, even in the face of violated assumptions. If we have a robust model, then we don't have to be so reliant on possibly shaky assumptions. The sample median is often cited as a robust estimator for a typical value in a distribution compared to the mean. We often hear that the mean is unduly influenced by outliers in a dataset, and this is true, but what assumption do outliers violate? Many times we assume a distribution to be normal. Normal distributions have the property that most of their probability is concentrated near the mean. You often hear this phrased as the 68, 95, 99 rule. Outliers challenge this concentration. If there's a possibility that there can be many outliers, it poses a danger that the data may come from a so-called heavy-tailed distribution, where extreme events are more likely, and this would violate the normal distribution assumption. In causal inference, there's a technique called propensity score matching. Propensity score matching is used to try to match people in a treatment group to people in a control group who are very similar to them. By doing this, you can produce estimates that better resemble a causal effect. Propensity score matching requires two models. One model to estimate the effect of the treatment on the outcome, and another to produce a score that is used to match people together. Both of these models have to be correctly specified for the results to be useful. Correct specification essentially means that we choose the correct model for its purpose, but this is almost never the case. To account for this, there are robust versions of propensity score matching that allow for one of these models to be wrong. The less assumptions we have to make, the better. We have to make sure our models can actually account for this. Yes, you read that right. We're done with the theory, we're done with the computation, we're going back to plots and visuals. Plots give us a way to examine our data and assess our statistical models. It's just easier to learn from your data if you can look at it rather than just have it in a CSV. But it's undeniable that the skill is an important part in any statistician's or data scientist's toolkit. There's even an entire paradigm of R programming dedicated to formalizing exploratory data analysis. There are people who code in boring base R, and then there's people who code using the tidyverse framework, popularized by the god Hadley Wickham. The tidyverse set of packages makes it extremely easy to get your data into R, clean it, and visualize it. I highly recommend learning it, and I hope to have a more in-depth video on it in the future. What does it mean for an idea to be important? At first, I thought that a statistical idea would be important if the paper that introduced it was cited many times. But this was not the case. The author specifically mentioned avoiding citation counts. Rather, they view important ideas as those that influence the development of ideas that have influenced statistical practice. I highly recommend reading the original article. It's free to read online on Adriel Gelman's blog. You can just Google most important ideas in statistics and look for his name. This video only covers part of the article. It's full of citations, so readers can pick it up and read more about a particular bullet point that they were interested in. Other articles have even performed actual statistical analyses to answer this question. If you think the authors missed a cool idea, tell me about it in the comments. I hope that I've showed you that statistics didn't stop with the two-sample t-tests and linear regression. New technologies create new types of data, so statistics needs to innovate to keep up. If you think I've earned it, please like the video and subscribe to the channel for more. I've also started a newsletter to accompany the YouTube channel so that people can get my videos delivered straight to their inbox. I'll see you all in the next one.